Advanced Studio Classroom is on the air. Join us today as we talk about one of the most difficult topics we've ever talked about. Hello, listeners. Welcome back to another Advanced Studio Classroom. It is May 17th, 2019, and I am your host for today's program. My name is Simon. You are joining me for our Newsworthy Clips article for the month of May. Those of you who are regular advanced readers or listeners, you will know that newsworthy clips are basically a collection of smaller news stories. And so today we are looking at the second of those stories. It's called Quantum Computing and the Fight Against Hacking. And that first term there, quantum computing, that is the subject that makes this one of the most difficult articles we've ever discussed on the air. So we are excited to have you here with us in the studio. When I say we, I am talking about my two panelists today. We have Josh back in the studio. Welcome, Josh.
Thank you, Simon. As always, it's good to be back here on Advanced Radio, and it will be interesting to try and tackle this subject today.
Excellent. And we also have Manya. Manya, welcome back.
Thanks, Simon. I'll be honest right now, I don't know what quantum computing is.
It is a tough subject, I'll tell you. I mean, basically, when you look at that title, right from the beginning, when I read that, I was like, what on earth are we talking about? But fortunately, we have Wikipedia at our disposal. And so they have a number of actually very easy to read articles and some videos that offer good explanations of some of the ideas here. And so I would encourage you listeners, if you are confused by the things we are saying, to go and do some of your own research. We'll try to give you a rough estimation of what these different terms mean and what ideas are represented here. I guess for you, Manya, we should start with this word quantum. And basically a quantum is the smallest of a physical thing, the smallest form of a physical thing you can have. So what do I mean by that? Already that's confusing, right? When you think about growing up and going to chemistry class, they told us that everything was made of atoms. But of course, then they told us that atoms were made up of smaller things like protons and neutrons and electrons. And so those are smaller things. And now, of course, we know that those things, like electrons, are also made up of smaller things. And so the idea here is that when we're talking about a quantum, we're talking about the smallest of the things that you can get to. Now, quantum computing, that's a little different. Josh, how does that compare to digital computing, like computing we have now?
Well, that's a very good question, Simon. And that also brings up a problem in that the computing language that we have now is also difficult for a lot of people to understand. So right now, all computing is done in a binary form. So that's a machine language that understands everything in terms of ones and zeros. So it's really quite impressive that you can have a 3D computer video game that has lots of different things going on, that the machine that is running that video game understands in terms of a series of nothing more than just ones or on or zeros or off. So that is the digital form of binary machine language that we all use every day, even though we're not aware of it.
Well, how does this relate to quantums? I guess the idea there is that, Josh, you mentioned that there are ones and zeros, ons and offs. Mm-hmm. And the way we measure that in the technology is actually with electrons. Sure. Because electrons, like electricity, right? They have a charge, like a positive and a negative. And so you'll notice if you ever take your computer apart that there are big magnets, very, very powerful magnets that make wonderful fridge magnets that will never fall off your refrigerator, right? And so we have these very powerful magnets because they're manipulating the position of the electrons to create these ones and zeros. Now, with quantum computing, that's a very different thing because there's no ones and zeros, right?
There are a number of possible positions that could mean different things in relation to other possible positions. So what it does is it
Well, not just on and off, like the 1 was on and the 0 was off, but it's like kind of on, a little bit on, sort of on, mostly off, kind of off. And so there's like a whole
or even
scale.
turning towards off or turning away from off. So there are a lot of different possible positions that are moving towards on or off.
Now, I see you are confused, Manya. We'll try to clarify as we go on, but
I have a
before...
general idea of what you mean. Can I see if I understand?
Good stuff. Yeah,
Okay.
give it-
Okay.
Well,
I know.
it will be
so,
a machine. Your
okay,
quantum
it will be a
computer.
machine. So it's like the thing
Yeah.
that builds the machine. That like.
The quantum computing, they don't really exist yet. It's kind of an experimental idea, things people are working on. But the idea is it would be a computer that instead of encoding everything as ones and zeros, ons and offs, would use quantums.
Okay, okay.
So things that are smaller than just the electron. And the special thing about sort of quantum physics is that things aren't ever just one thing, like on or off. They can be kind of on and off at the same time, and all of these weird sorts of ideas. But actually, you don't really need to understand the weird sorts of ideas to understand why this is useful in the fight against hacking. And that's kind of what we're talking about here in this article. So without delaying any further, listeners, let's get into our first reading. You will find it on page 29 of your Advanced magazine for the month of May. We're going to look at the left-hand column, actually the top part of the left-hand column, and do that reading now.
Quantum computing and the fight against hacking. Researchers from the University of Illinois are joining Chicago area scientists in creating a network that could pave the way for communication that can't be hacked. The effort is part of a push from national labs and universities in the state of Illinois to establish Chicago as a leader in an emerging field of physics and engineering called quantum technology. Quantum research involves studying matter and energy at the smallest possible scale. Experts say advances in the field could have far-reaching implications, such as eliminating cybersecurity risks and expediting pharmaceutical discoveries. The field has the attention of tech giants and the federal government, but, so far, most of the breakthroughs have occurred in the lab.
Okay, so we begin here with some discussion of research that's going on at University of Illinois. And of course, this research, we find, is being done to pave the way for communication that can't be hacked. Now, Manya, when you pave the way for something, does it mean you do the thing? What exactly does that mean?
No, it's kind of like you're making the way. You're building the road so that other people can be on that road.
So you're like preparing for the communication, right?
Yes.
Okay, so basically what we are finding out here is that these researchers, they aren't creating a quantum computer. They're not using quantum computers. They're sort of doing the research that eventually will allow people to do computing in a way that it can't be hacked. So this, of course, is a big national security issue, right? We hear a lot about hackers and people breaking into computer systems and stealing information and causing all kinds of trouble. And potentially, this quantum computing could help avoid that sort of thing. So we learn in the second paragraph, this is an effort that's part of a push. A push is like a big effort, a big coordinated effort from national labs and universities in Illinois to establish Chicago as a leader in this emerging field of physics and engineering called quantum technology. Now, when something is an emerging field, Josh, what do we mean by that?
So we mean that it's new and that it's developing.
So this kind of fits with the paving the way for things, right? You're in the process of preparing for something. And that's really what they're trying to do. They're trying to allow Chicago to be well positioned as a city, to be in a good position, to be a big important center for quantum technology. And they're doing that by developing all kinds of research and facilities and things like that in the area. We see in our third paragraph, what quantum research is. Now, Josh, I think you are probably best suited here to give us a rundown of this paragraph. What are they doing in this quantum research?
So here, this is sort of going towards the explanation that you gave earlier on in the program, where quantum research involves studying matter. So that's all things with physical properties at its smallest possible scale.
So the smallest thing
Exactly.
we were talking about.
Within the matter. So as Simon had mentioned before, for a while, we had talked about atoms and electrons and neutrons sort of being like the smallest thing that we can detect. But then as science progressed, we found that there were smaller and smaller and smaller things. And now we're talking about quantum material, which is the smallest possible thing.
Now, the experts are saying that advances, so improvements in this field, could have far-reaching implications. Now, implications, of course, are effects, but when we say things are far-reaching, Manya, what do we mean by far-reaching effects or implications?
That means they can have a really big effect and it could go really, really far.
And maybe in surprising ways, right? Like in this article, we're talking specifically about the fight against hacking, but they mention here that it could also do things like expediting pharmaceutical discoveries, meaning making discoveries of new drugs quicker and easier. So all kinds of benefits that you maybe can't imagine at this point. It tells us that the field has the attention of tech giants. Now, when we say tech giants, are we talking about large people who are good at computer programming?
No, we are talking about big organizations that are important in the field. So, for example, Google would be considered a tech giant.
Okay, and so this has their attention along with the federal government. But most of the research and breakthroughs so far have come from labs, right? So research labs, universities, places like that, right? Okay, that brings us to our second reading where we talk specifically about this project that they're working on in the Chicago area. So listeners, join us again in your magazines as we look at the bottom part of the left-hand column on page 29, and we'll actually read until we continue over to the top of the right-hand column. Let's do that reading now.
That's where this project from Chicago area scientists is attempting to make progress. The scientists plan to use a 30-mile-long, unused network of high-speed optical fiber that stretches between Argonne National Laboratory in Lamont, Illinois, and Fermi National Accelerator Laboratory in Batavia, Illinois. Particles of light will travel back and forth on the underground fiber between objects at each lab. That connection, called entanglement, allows communication between the two objects without moving them.
Okay, so we get our first sneak peek into what they're actually doing in the Chicago area here. And basically, I suppose it sounds almost like they're setting up a phone network or an internet. Right, Josh?
It does here. They're talking about using a 30-mile-long unused network, so a network that exists but is not being used for any particular reason, of high-speed optical fiber.
Now, that's kind of special fiber, because I suppose when you're setting up a telephone network, we usually use copper wire, right? But when we say optical fiber, that word optical, it means like something you see, right? When you go to the eye doctor, that person's called an optometrist or an ophthalmologist because they specialize in things that are being seen. So optical fiber, this is a wire that lets you see things, right? And I suppose the common term we use when we're talking about things like this is actually fiber optics. That's sort of like a term we hear a lot, right? Fiber optic cable. Is that the same thing, Josh?
Yeah, it's the same thing. It's a cable that's designed, instead of transmitting just electrical impulses, it's designed to be able to transmit pulses of light.
Yeah, so you actually see these often in decorations for light shows, right? They're kind of dangling, clear-colored cables, but if you look at the end of them, you see bright, different lights kind of coming out. So the way I see them most often these days is actually in decorative stuff. But they, of course, were developed for a very different purpose, right? And that's what we're sort of seeing here. Now, I don't know why this 30-mile-long network is not being used, but I would imagine it's from a former research project, because the cable is already laid. It stretches between what are actually some very famous government and I guess maybe university involved, but government laboratories, basically. Can you tell us what the laboratories are, Monia?
They have the Argonne National Laboratory and the Fermi National Accelerator Laboratory.
Okay, so we have these two big laboratories where a lot of research is sort of done, and they have this network between them that isn't being used. And so now scientists are going to use this. What are they going to use it for, Josh?
Well, they're going to use it in order to send light back and forth in order to transmit information.
So they're going to send light down this cable. Specifically here, they use the term particles of light. And for those of our listeners who are kind of science buffs and interested in science, you will know that particles of light are called photons. And that actually is important to this whole quantum story, because we mentioned when we were discussing the difference between computing we do now, digital computing, and this idea of quantum things, that digital computing uses electrons to push things into this binary 1 and 0 position. Now, a photon of light is something that's smaller than an electron. It's part of this quantum physics thing. And so it means that basically what they're doing is experimenting with a kind of moving of, I guess, information. I don't want to use the word thing, but they're moving information using this sort of quantum system. That's what they're trying to do, right?
They are. And so they have a very specific way that they talk about the information in this particular system and this connection in this network, which they call entanglement.
Yeah, that is a tricky word. They actually get into entanglement right in the last sentence here. They say that connection called entanglement. And so this word entanglement, it seems very innocent when you read it in the text here, but this is really the doorway to the discussion about quantum physics in this article.
It's true. So if something is entangled in something else, it means that it's caught in something else, like being caught in a web or being caught in a net or being caught maybe in a sweater.
I think of shoelaces all tied together and spaghetti.
That's
all
right.
knotted together. So where I don't know if you listeners have ever played a kid's game called Pick-Up Sticks, but this comes to mind right away for me. Pick-Up Sticks, basically you pour out a bunch of sticks. They're kind of like chopsticks, but you pour them out into a pile and you have to remove them one at a time without making any of the other sticks move. And it's very difficult to do because they're resting on each other and they're all entangled. They're involved with each other. And that's basically what we're talking about here, how these quantum particles, these quantum things, are all affecting each other all the time. And that situation where you can't look at just one of these particles because it's being affected by all of the other ones, that's what we mean by entanglement, right? Okay. And so this connection, this entanglement, allows communication between the two objects without moving them. Now that is confusing. But essentially what I take from that is instead of moving an actual electron from one place to another, what you're doing is you're having an influence on the other thing without necessarily having to move it anywhere.
That's exactly right. One of the things that's very confusing about quantum physics or quantum relationships is that it seems to not make sense in a day-to-day way. So how can I affect something here and have it create an effect on something else when there isn't any clear connection between the two?
Yeah, and I mean, you get into this sort of discussion anytime you're in a physics class, I suppose, especially a higher level physics class where just most of the people in the class are confused because our real life experience tells us that if you take your hand and you push the cup will fall over. But what they're basically saying in quantum physics is, you're able to knock the cup over without actually touching it because you can have an influence on the state or the position of that thing. And that's kind of the idea of quantum physics. Now, I guess, how is that happening? Well, it's happening because it's happening at such a small scale where things aren't really touching. Like when you think about yourself touching the cup, maybe you're not really touching it because the atoms in your hand aren't actually banging into the cup. The atoms in your hand are having an effect on the atoms in the cup. And so it's kind of making this mental leap that is a very difficult thing. But nonetheless, that brings us to an example they give us in this article, which we find in our third reading. So join me on line 5 in the right-hand column of page 29, and we'll read through to the end of the article and then try to make sense of it together.
Imagine a magnet at Argon pointing in a certain direction, said David Oshlam, the University of Chicago professor and Argon scientist leading the project. The network could be used to teleport information about which direction the magnet is pointing to Fermilab. It is called teleporting information because we move the information, not the object itself, Oshlam said. If someone looked at or hacked the information being communicated, the information would change or be destroyed. Scientists in the field work to understand the properties of atoms, which often behave in ways that are counterintuitive to people's normal perception of physics. Oshlam explained it this way. If I told you in a quantum world that if you threw a basketball against a wall, it would go through, you'd say, "That's ridiculous," he said. Things like that happen on a quantum scale all the time.
Okay, so they lay out this example for us here, and it's in some ways similar to the examples we have talked about already. They say, imagine a magnet at one of the laboratories pointing in a certain direction. So if it's a magnet and it's pointing somewhere, it's going to be influencing things with the magnet in that direction, right? And then the idea is that they are communicating information about which way the magnet is pointing through this network. And then they use this term here when they talk about how they're communicating. They say, teleport information about which direction the magnet is pointing. So when we say teleport here, Josh, what are we saying?
So we mean instantly move from place to place without passing through the space in between.
Yeah, so no time being spent, right? Like moving from place to place. So we're sending this information about which way the magnet is pointing. And they tell us in the next paragraph, there's a quote. It says, it's called teleporting information because we move the information, not the object itself. So the information is moving through the network. And how is that different from now? Well, now the information is encoded into electrons that are moving. So the actual electrons are moving as opposed to the information moving. I guess the way you would think about this is with a digital computer, if you want to talk to a different digital computer, you put what you want to say into this code of electrons, you send it to the other computer sees it and then decodes it to understand what you're saying. Is that right?
Yeah, so I would say maybe here, if you're thinking of the instructions you would send to a computer to say, we're going to point a magnet in a certain direction. And those instructions are coded in such a way that you can take those instructions and send them to another computer in another area. And that computer can decode the instructions and understand what you've done, right? Then you're actually sending instructions back and forth, right?
And here, in this quantum computing, there's no stream of electrons, basically. Right. And that's sort of what affects this idea of fighting against hacking. Because they tell us in the next section there, if someone looked at or hacked the information being communicated, the information would change or be destroyed. Now, there's an example of this in technology. It's a thing called Van Eck phreaking. It's spelled VANECK, and then phreaking is PHREAKING. And it's just this weird spy idea where it's like you can set up a sensor on one side of a wall and pick up the electronic signals coming out of, say, a computer screen on the other side of the wall. And you can use these signals because there's all these electrons moving around in our computer. So you can use these signals to reconstruct what is on the person's screen. So it's like someone can read your computer screen through a wall just based on the electromagnetic things your computer is doing. Now, if you remove the electrons from that, people can't spy on you in that way. If they try to interfere with it, then the signal is destroyed. It's disrupted. And so that, I guess, is basically the idea here. If you remove the electromagnetic part from this computing process, you remove the ability of hackers to influence or spy on or read that information. Mm-hmm. Are we agreed about that?
Yeah, I would say that's a pretty rough idea of what's going on here. I mean, like we say, listeners, this entire field of spreading information around is very counterintuitive, right? So it's hard to, sometimes you would say, wrap your head around it, meaning to really understand what's going on here.
That's right. And frankly, we are editors, so this is the best we can do, even if it's not perfectly correct. Mm-hmm. As we move into our last two paragraphs, we see that scientists in the field are working to understand the properties of atoms, which often behave in ways that are counterintuitive. Now, that's actually just what you said, Josh, mm-hmm. to people's normal perception of physics. And so then we're given this example that is an example of how counterintuitive this quantum stuff is. The person says, if I told you in a quantum world that if you threw a basketball against a wall, it would go through, you'd say, that's ridiculous. And that's how we kind of feel about this idea of, not sending a thing. But he says things like that happen on a quantum scale all the time. So basically, the way things are really working is very different from what we think is the way things are working. Mm-hmm. And that allows this opening to quantum computing and hopefully a hacker-free future. Listeners, if you have any comments about today's article, please feel free to send us a letter at letters@studioclassroom.com. You can also jump on Facebook and go to our Facebook page and talk to us that way. Until next time, thank you for joining us today. My name is Simon.
And this is Josh.
And I'm Manya.
And we're saying bye for now.
Bye.
Goodbye.